just to see what kind of error message I get. Now, this is another thing that you can do is intentionally try to introduce errors so you can see what error message you should be getting. So when you do see the error message, you know what to do with it. And it will say number of operands mismatched for move. It's not telling you you're missing a comma.
Yes, I mean, you think they've given it one operand.
Yeah, but this is a good exercise. Intentionally putting syntax errors into it is a good thing because it gives, because you already know what's wrong with it. You're just trying to associate the problem with the error message. Now, if you don't do this and then you accidentally make a mistake, then you'll be going like, okay, what does that mean? Who's missing an operand? Why is it missing an operand, right? I distinctly see two things after the instruction. Why is it missing it? Okay, assemble. Okay, I have another problem here. It is on line 13. Oh, okay, it's complaining about the multiplication. Why would they complain about that? Oh, because we have two things that are undefined. Okay, invalid operands, ABS, and dot data section for the asterisk. Okay, I can tell you exactly why it is having a problem. Nope, that should not be a problem. Oh, I can see it. Because L1 is actually in dot data, but L2 can be anywhere because it's just a definition. So because it's floating, there's no way for it to actually know at that time what it is. So I cannot do that. Okay, let's just do something else. Assembled, linked, and then we'll use GDB to approach this problem. Put a breakpoint on line 10. And this time, what I want to do is to look at L1 and L2 again. Okay. Well, we can print L1. Okay. When we print L1, it's actually printing the value at the location indicated by label L1. Okay. So if you look at hexadecimal 1, 2, 3, 4, 5, 6, 7, it is actually that particular value in decimal. Okay. Well, how do we print that number in hexadecimal then? Well, you can first of all you can say help print. Okay. Help print gives you this gibberish. You can read it on your own, but I can do this because I already know it. You can print /x. It will print it in hexadecimal. So you will print in hexadecimal, and you ask it what is the L1. It gives you 1, 2, 3, 4, 5, 6, 7, which is correct. Okay. Yep.
If you assemble this without the G stabs, will it not work in the debugger? Is that what happens?
That is correct. If you assemble without G stabs, then the symbol table will not be in the object file, nor the executable. So you will still be able to get into GDB, but GDB cannot associate memory locations with lines in the source code anymore. Yep. All right, so let's go ahead and print L2. What do you think will happen when you try to print L2? It's treating L2 as if it is a variable. Is L2 a variable? No, it's just a label designed to be some gibberish, right? So the debugger doesn't know any better. The debugger thinks, oh, L2 is another variable. So it will go to a memory location at the address specified by the label L2. But L2 is not a valid address. It is not valid from our perspective because this process does not have permission to get to that particular address. So when you try something like this, it just barks at you and go, can't do that because that memory location is not ours. Is that okay so far? Now we can do something else. We can say print the location or the address of L2. And once again, this is actually mixing, concepts, but there's no way to get around it. But it will tell you that that location is, 2B162, which in decimal is the value that we specified. Are we doing okay so far? Yep.
Is it possible to get part of L1 or L2 without doing direct access?
Okay, are you talking about the label or memory locations starting at that label?
Talking about the bit.
The bit? No, you cannot get to it unless you use bitwise operators. so you have to shift and mask and stuff like that. Normally, you don't have any need to do that. Are there any other questions? Other questions? Okay. So I'm just going to go through some other skills that you will need for your homework assignment. For your homework assignment, the first thing you need to do is to really get familiarized with the examine command, because you want to be able to interpret bytes in memory as bytes, as words, as 32-bit words, print it out in hexadecimal, print it out in decimal, and so on and so forth. You know, be able to do base conversion and stuff like that. Now you can do base conversion using a calculator, but since you're already in GDB, you can just use GDB to do base conversion. For instance, you can say print /x to mean I want to print the value in hexadecimal, and then you can give it, you know, something in base 10. It will tell you what it is in hexadecimal. You can also just say print and then give it a hexadecimal value. And it will give you the decimal representation. In other words, without a slash, it is automatically using base 10. Okay? And you might find this to be useful. Hint, hint, hint. Okay? There are other tools that you might find helpful too. So let me go ahead and look at the program again. Now, if you list again, it will pick up from the last time we listed the program. If you wanted to start from line 1 again, just say list 1. Then it will start from line 1 again. Okay, so you might find it helpful to look at these bytes in different ways. Okay, so I'll just give you one particular idea. Okay, you can say x slash. This is a 32-bit thing, so we can always look at it as 32-bit. Remember, word W in the debugger means 32-bit. X means hexadecimal, and you can just use L1 in this case, not $L1. Because the debugger, using the examine command, it is actually looking at L1 as the value of the label, but not the value at the location of L1. And nope, it's making that mistake. We actually have to use $L1. But remember last time we didn't have to. Okay. Okay, so this will tell you, this is really useful. This is the address. This is the address at that location in memory. If I look at it as a 4-byte thing, as a 32-bit thing, it will be representing this particular value in hexadecimal. Are we doing okay so far looking at that line? Okay? If you don't want to look at it as in hexadecimal, you can always say, well, give me the decimal interpretation as unsigned number. This will give you the unsigned number. You can also say, I don't want to look at those 4 bytes as one 32-bit thing. I want to look at those as 2 16-bit things, and each one printed in hexadecimal. So that will say 2HX. The 2 means I want to print 2 items. H means each item is a half word. In the debugger, a one half word is a 16-bit item. The X means I want to print it out in hexadecimal, format. So this is printing this. Is that surprising to you? If you understand, little endian, this is not surprising, because out of these 4 bytes, this is the least significant byte. It will have the first address. This is the second least significant byte. It will have the second address. But looking at this as a 16-bit value, this one is the least significant. It has the least address. So it does match up, because the least significant byte is the first one in the memory location, and this is the second least significant byte. It has the second location. Okay? So when you look at this, and if you think that this is, I don't think it should look like this, then you really need to kind of think about it and try to reinterpret or try to think what it means to be little endian, because this is correct. All right. Or you can look at it as 4 things. Okay. Each thing is a byte, and I want to print each byte in hexadecimal. Oops. Ampersand. That one. Yep.
So for the second X, that puts it back into decimal again?
the second X?
Yeah, so you go x/wx, that in L1, and it prints out the decimal that way, but if you take off the second X, it prints it in hexadecimal.
You mean
Yeah.
you mean this X here? So the default is hexadecimal, right?
Yeah.
Yeah, so
Uh-huh.
I think that means the default is in base 16. Okay? You can also do something kind of funky, okay? You know, what funky things are we talking about? Okay, so, okay, I think we have a little bit of a problem here, because if I add 1 to it, it is off by how much? Okay, let me clear the screen first. Okay, and we'll do this first, and then we'll do this one. Look at the addresses of these two lines. They're off by how many bytes? 4 bytes. Why is it off by 4 bytes when I say add 1?
Because you're doing 4 bytes.
Because the implicit type is int, a 32-bit int. So what if you want it offset only by 1 byte? You have to cast it, add 1. So you have to do something like this. You have to do a cast to a char pointer, then it's off by 1. Okay? Now it's still complaining cannot access memory at location something. Why do you think it's complaining? Exactly. Our data section only has 4 bytes, and it's trying to print 1 byte beyond that 4th byte, which does not belong to this process. Because according to the linker, this process only needed a 4 byte data section, so the rest of the address range is not accessible. Very good. Yep.
Ampersand means dereference?
The ampersand in C and C++, also in
Yeah.
this context, means the address of.
Wait, that's, you're getting the address of L1.
Because the
And
debugger,
then it displays the value?
because the debugger mistakenly understands L1 as a variable.
Oh.
So we have to kind of trick the debugger to think that L1 is the address label again by using the ampersand symbol. All right. Are we still doing okay so far? All right. So what we'll do next is, for the next, 8 minutes or so, I'm going to go back to the homework assignment. And what we'll do is we'll take a look at the homework assignment again one more time. Oh, actually I don't have to do that. I have it already here. Let me open up another tab, go to find it, and take a look at that code. All right. According to the instruction, let me expand the screen so we can see the entire thing. Okay, so according to this, I want EAX to contain this particular bit pattern after these 3 instructions here. Okay, remember the first operand is what you need to change, so this is definitely nowhere close to the final solution. And I can also tell you that there's no unique solution in this case, okay, because things are just relative, okay? Everything is relative. So how would you approach this problem? Well, first of all, we want to lock down some of the instructions first. In other words, there is only one way to lock down the most significant 16-bit of EAX. Okay, look at these 3 instructions here. Turn on line numbers again. Okay, so on lines 18